Students go to the top of some bleachers and they drop a ball, and the bleachers are measured to be 4.3 meters high. We're asked how fast will the ball be traveling before it lands. One thing to note here, we notice that we're not told anything about the mass of the ball. The mass does not affect how fast the ball will be traveling before it lands. This was actually discovered by Galileo hundreds of years ago, that the mass of an object does not determine how fast it will fall. So we're working here with constant acceleration due to gravity. So some things that we should do initially is just write down some values that were given. If we drop a ball from the top of the bleachers, what would the initial value be of the velocity? Would the ball have any velocity if we're dropping it from the top of the bleachers? Well, no, the ball would start from rest. So we can say then that the initial velocity of the ball is 0 meters per second. It's not moving when we initially drop it. We also have learned then that the acceleration that we're working with here is g, and g is equal to 9.81 meters per second squared. So this is the acceleration due to gravity anywhere on Earth. And we're told then that the ball is going to fall for 4.3 meters. And what direction is that going to be? So we're interested now in a change in the height of the ball. Well, if it starts from some position that's more positive and it ends up at some position that is smaller, so I'm saying here, if this is the y-axis and this is positive, positive being upward, and the ball starts here at the top, and then it travels and ends up towards the bottom here, well, this is 0. So our initial is some bigger number, and our final is some smaller number. So delta y is defined as y final minus y initial. Well, my final is actually here at the ground, at 0. So my final is 0. And where did I begin? Well, I began at 4.3 meters high. So y final minus y initial means 0 minus 4.3 meters. And this tells me then that my delta y, my change in y, is in fact negative, minus 4.3 meters. So this is our starting information. We don't have anything telling us the time. We don't know what the time is. And we don't know what the final velocity is. That's what we're trying to define here. That's what it asks us in the problem. And let's write down our two kinematic equations. So the ones we've learned so far are v final equals v initial, this is our initial velocity, plus how the velocity changes. Previously we've called it AT, and now I'm going to call it GT because we're interested in the special case where A equals G, which is the acceleration due to gravity. And the second formula that we have is delta y is equal to, now we have our initial velocity times time. This is the rectangular component of the velocity versus time graph, plus the triangular component, which is 1/2 gt squared. The a becomes g because we're working again with the special case of the acceleration equal to the acceleration of gravity. So these are my two kinematic equations, and these are all I need to solve the problem. I don't really need to create a velocity versus time graph, although you could create one and you could solve the problem geometrically. But I'm going to solve it just using our two kinematic equations. So I need to look at these kinematic equations and I need to say, okay, well, what do I have and what don't I have? So this first kinematic equation requires some final velocity. Well, that's what I'm trying to solve for. that's what the problem is asking. How fast will the ball travel before it lands? That's its final velocity. So I can't initially use this top equation. So let me take a look at this bottom equation. So I have a delta y. I have an initial velocity. We know that's 0. I don't have a time, but if this initial velocity is 0, well, this term right here is 0. And I know the value of g. The only value I don't know is t, and I have all the other values, so I can solve for t. So let's do that. Now, the first thing I'm going to do to make this simpler is if vi is initially 0, I don't have to be worried about this first term. I can get rid of it. Vi is 0, so this term is going to be equal to 0. I'm not even going to bother solving for it. You have to be careful making this assumption. I have to look here and analyze this equation and say, okay, if I didn't solve for t, but I first put all the numeric values in, the delta y, the vi, and the g, I could do that and then solve for t. Therefore, I can say, okay, well, if I put 0 in here, this term is 0. So if I solve for t first, I don't even have to bother with this term. It's 0. I know it's 0. So you have to be careful making an assumption like that, but I'm going to go ahead and make that assumption. I know this term has to be 0. So when I solve for t, I now have delta y equal to 0 times t plus 1/2 g t squared. So the only value I entered here was 0. I did that because I wanted to make this easier to solve for t, and so I just get rid of this term. So this then becomes delta y equals 1/2 g t squared. I multiply both sides by 2, so I have 2 delta y equals g t squared. I divide both sides by g, and I have 2 delta y divided by g equals t squared. And now I take the square root of both sides of the equation. The square root of t squared is just t. And then I have the square root of the other side of the equation, which is 2 delta y over g. Okay, now I can put my values of delta y and g in. So I'm looking at delta y, which is this, and g I know to be 9.81 meters per second squared. And when I introduced g, this value of 9.81, I said it's typically negative. Does that make sense? Should this be negative? Well, if I leave it as is, I know that I have a delta y that's negative. And if that would be the case and g would be positive, I would have a negative number under this radical. I can't take the square root of a negative number. That's an imaginary number. I can't do that. I need time to be positive, and I know that g is pointing in the direction of the Earth. G points downwards. Why? Because if I drop something from some height, it's going to accelerate downwards. It accelerates towards the Earth. So g needs to be negative, and delta y is negative. And when I put those values in, I have 2. My delta y is negative 4.3 meters. And my g is negative 9.81 meters per second squared. I look at my units before I do anything else, and I see I have meters in the numerator and a meters down here in the numerator. So those divide out to be 1. And then I have a 1 over a second squared. Well, I know from my complex fraction rules, if I have a 1 over something under a fraction, then I have to flip this. So I can get rid of my negative signs. 2 negatives is a positive. So I've gotten rid of my negative signs, and I'm left with 2 times 4.3. The meters divided out, the 1 over second squared means this second squared comes up here to the numerator. And I have a seconds squared over 9.81. Again, the negative signs disappeared because I have a negative divided by a negative. Now I can put all these numeric values in my calculator, and I'll do that. So 2 times 4.3 divided by 9.81. And I get a decimal value. So this is going to be equal to the square root of 0.88. I'm rounding to 2 decimal places, and I still have my seconds squared. Now I take the square root of 0.88, and I'm using the value prior to rounding to 0.88, and that gets me, this is equal to 0.94 rounded to 2 decimal places. Square root of seconds squared is just seconds, and that's exactly what I want because this is our time. So this is the first important value that we solved for. And we started with this equation right here. So that equation helped us find time. It was the only unknown. So now we have the time. So now I'm looking back now at this other equation, and I'm saying, okay, I have an initial velocity, it's 0. I know what g's value is, and now I have a time. So I can solve for this final velocity. So my next step now is v final equals v initial, which is how much? How much is v initial? Again, just like in the first step, v initial is 0. We're starting from 0 velocity. And now I have to say, okay, again, what direction is g pointing? What should my final velocity be? Well, if it's dropped from some position and it falls downwards, it's going to speed up until it hits the ground. So this velocity vector is going to increase over time. Just like if you would jump out of a helicopter or an airplane, you would start at 0 velocity, but you would be going very fast by the time you reach the ground if you didn't pull your parachute. So our final velocity should be negative since we're moving towards the ground, and it's going to be larger than our initial velocity. So I need a negative acceleration. I need to put a minus sign with this acceleration because the acceleration is pointing downwards. And it's negative 9.81 meters per second squared. And my t for time I found in the previous step as rounded to 0.94 seconds. And do my units make sense? Well, I have a second squared and a seconds. So a second squared can also be written as seconds times seconds. And if I have a seconds times seconds in the denominator and 1 factor of seconds in the numerator, I can divide 1 factor of seconds in both the numerator and the denominator, and I'm left with meters per second. That's good. That's what I want. Meters per second is the correct unit for velocity. So then this is equal to negative 9.81 meters per second times 0.94. So now I'm going to put that into my calculator. I have a negative sign, 9.81 times the previous value for time that I found. And this comes out to be negative 9.19 if I'm rounding to 2 decimal places, and that's meters per second. If you got a different value, it's because I did not round, I did not use this rounded value when I calculated this final multiplication right here. I used the value prior to rounding to 0.94. So I got negative 9.19 meters per second. And this is the final. This is the final velocity of the ball having dropped it from the top of the bleachers. So hopefully this makes sense to you. We started at 0 meters per second. We're falling downwards. So if we're falling downwards, we're going to have some sort of negative velocity. Our acceleration, g, we had to be sure to add a negative sign to because g is pointing towards the Earth. And like I said, when I introduced g, it's typically pointing towards the Earth, and so that's typically downwards. If we're working with a traditional coordinate system where y, the positive direction, is pointing upwards, then g has to point in the opposite direction.